right? Lecture 6, and the slide is about what is the effect of this mesh 1D, 2D, or 3D? What is the effect of these elements on meshing and also on the resultants? If I go for one example for understanding that first we'll take, and thereafter we can move for the next point, because as I said in the second unit we are going to talk on meshing only, because the unit is meshing techniques. So if I go for what is the effect, then here you can see that second order tetrahedral mesh featuring additional mid nodes for improved deformation accuracy often yield better results compared to the first order mesh, particularly in capturing sharp curves more effectively. What is the meaning of this statement is second order elements are having extra nodes, and due to which the deformation after the solver, you will find that there is a deformation in the mechanical member. That deformation is more accurate compared as to the first order element if used for meshing. So in the diagram form you can see that like this, that if you can see my cursor here, you have tetrahedron like this, tetrahedron element, 3D element. This is 3D element if you remember that list. If that is used, so this first case light blue is mesh before or element before deformation. Same that is shown here by yellow lines, right? And this is first order, and this is second order tetrahedron element. You can see nodes are more, 10 nodes. Here we have 4 nodes. So these 10 nodes and 4 node element are before deformation. After deformation, when it is first order, after deformation it look like this. After deformation it will get expanded due to the forces acting and deformed form. Whereas in second order tetrahedral element case, you can see that deformation here is having some curve, and actual deformation or bulging is like this only. Okay, so this shape is more nearer to the actual compared to this shape. So therefore, second order elements are comparatively more beneficial compared with the first order. But the drawback is it takes more time, more computational time, and therefore it will take time for analysis. Similarly, if I go for geometry case, you can see the first order tetrahedral mesh if used. You can see, suppose there is a hole inside a plate like this. So you can see the curve. Actually, the hole is look like a polygon. It must look like a curve actually. But instead of using first order tetrahedron, we will use second order tetrahedral element. So in that case, the curve is like this, very sharp or nearer to the sharp. It is not actually very sharp, nearer to the sharp. When you go on increasing that number of nodes, you will get this curve sharper and sharper, which gives the refined and precise results actually. So in this way, the selection of element for meshing matters a lot in analysis, and therefore it depends on that what actually analysis you are going to do, how precise you require it, or you just want overall values so that you can predict on that particular values only. Depending on this, you have to select the element. If you want very precise, then you need to go for a higher order. Whereas if you are compromising for that precision, then you can select the first order. The advantage will be faster you will get the result, and in higher order you have to wait for the result. So moving forward for the next point of our syllabus, and that next point is nodal unknowns and field variables. What is this nodal unknowns and field variables that we'll see? So in finite element analysis, that is FEA, degrees of freedom can be categorized into two types. One is continuous and second is called as discrete. So I'll explain that both in detail. Okay, in a continuous model, degree of freedom are defined as the infinitesimal displacement and rotation of a point within a structure. So this word, even if you used infinitesimal, it means a small, such a small that it is having a negligible length or negligible dimension. This infinitesimal is nothing but a smallest possible, which is beyond imagination. So this type of model, if is there, then we are calling it as continuous model, and degree of freedom. In that case, we call as continuous. Whereas, which is not possible actually. Okay, it is a hypothetical case, you can say. The practical cases, the degree of freedom are typically represented by functions of space and time, such that represented by function of space and time, such as displacement function or strain functions. That means in discrete case, we have the unit which is measurable. Unit means a small unit that you discretize it, like element. Measurable, and therefore it is possible for us to come out with some solution to that particular measurable elements or measurable units. So mostly we go for this discrete type of degree of freedom. In contrast, in a discrete model, degree of freedom are defined at discrete points. Okay? Within a structure such as the nodes of a finite element mesh, as I explained. Now, what is this nodal unknown then? Nodal unknowns are unknowns displacement values at each node in case of discrete degrees of freedom. So actually, nobody is going to ask you whether continuous or discrete. We are just going to concentrate on discrete only. And in discrete case, whatever the displacement at nodes, that values are called as unknown displacement values at that node are called as nodal unknowns. So on this also some questions are asked, and they are expecting some question also, or at least explain the nodal unknowns for 1D, 2D and 3D elements. Right? Nodal unknowns are typically represented as degrees of freedom. That means impossible for that node. Degrees of freedom is nothing but how much way the motion is possible. So degrees of freedom here actually going to represent as nodal unknowns. So in every case, element will have nodal unknowns and field variables. So first we'll see what is nodal unknowns, and then we'll go for field variables. The number of nodal unknowns in an analysis is determined by the number of nodes in mesh and the number of degree of freedom per nodes, right? So in two node 1D element, we have two nodes, and because it is 1D, each node is having 1 degree of freedom. When 1D, 1 degree of freedom. When 2D, 2 degrees of freedom. And when 3D element, 3 degrees of freedom. Right? So here number of nodal unknowns can be calculated from the elements. If it is 1D, 2 nodes, then definitely there will be 2 nodal unknowns and so on. Right? Like, for example, 2D analysis. In 2D analysis, nodal unknown typically includes the displacement in x and y directions, right? In 2D analysis. But in 1D analysis, we have only one direction. And in 2 nodes, then there will be 2. So in this way, in detail, I will give that to you in equation form also. From that, it is easier to get how many nodal unknowns that we have, right? So if I go for, so this is about nodal unknowns. If I go for field variables, these actually are the terminologies that we are going to use, right? Like when you are learning physics and you go for some terminology like velocity, acceleration, time, space, quantum, and quarks, electrons, protons, capacitor, resistor, energy, power, heat, work done, and so. So these are the terms that we use in that subject. In CAE, the term that we are going to use, we are understanding that now. Nodal unknowns and field variables are also some of the terms which we are going to use in the subject CAE. So nodal unknowns are the degrees of freedom or displacements at nodes, and field variables. Actually, I discussed for this field variable previously, and I'm just uh, what revising the thing again. Actually, at that time I discussed in brief. Here we will go for some details. So, if I go for field variables are continuous quantities that vary throughout the domain of the structure being analyzed. In simple word, I'll tell you that what is field variable is. It is just that parameters which we are going to measure during the analysis or after then at the end, the parameters that we are going to measure. So in case of structural analysis, mostly we measure displacement, we measure strain, we measure stress, so such parameters. Or in case of heat, we measure heat flux, temperature, and in case of computational fluid dynamics, we measure the flow of a fluid, we measure the velocity of fluid, pressure of fluid, and so on. In case of modal analysis, we measure vibration, its frequency, its amplitude, its wavelength, natural frequency, and so mode shifts like that. So therefore, uh, these parameters which we are measuring actually are called as field variables. So they represent the physical phenomena we are interested in, like stress, strain, heat flux, and velocity, and so on, right? And these field variable cannot be directly measured or calculated at every point, but we can approximate them based on the nodal unknowns. So this is the relation between nodal unknowns and field variable. So as I told you that nodal unknowns are displacement of the nodes. So from that displacement, we are going to calculate the deformation of your body, and in case of structural analysis, that displacement is going to show the temperature change. In case of heat analysis, that displacement is going to talk about velocity or flow in case of computational fluid dynamics. So in this way, the displacement which we actually call as a nodal unknowns are going to give you field variables, right? So, for example, the stress distribution in beam under bending can be calculated using the nodal displacement and the element stiffness matrix. Going for what are the types of these field variables? As I said, the parameters we call as field variables. So there are two type of field variables that we are going to have. And what are that? Primary field variables and secondary field variables. So actually, as I told you that I discussed about this both in one of previous session, and I at that time I have given very brief introduction or brief information about these two. So here we will go for that detail. Primary field variables. So that is red in color here in this slide, because on this slide we are going to talk for the primary field variable only. What is that? Primary field variables are field variables that are directly calculated from the nodal displacement. Right. So actually, nodal displacement is indicating that primary variable. That's it. So in case of stress analysis, structural analysis, displacement, deformation is directly calculated from nodal displacement. And from the displacement, we are going to calculate some other parameters, that secondary field variable. So like displacement, temperature, whatever directly we are getting from the nodal displacement, we will call that as primary field variable. These variables are often referred to as the primary variables because they are directly calculated from the nodal unknowns, which are the primary degree of freedoms, right? They are not derived from somewhere. They are directly calculated from the nodal displacement. Whereas, if I take in the case of secondary field variables, when we go for secondary field variables, in that case, this is the diagram for your information. Actually, I am showing. Uh, Secondary field variables are the field variables that are derived from the primary field variables. They are derived from the primary field variables. By some formula, by some relations, the primary field variable then after can be converted to uh, secondary field variable. Like you just see, what is modulus of elasticity is, modulus of elasticity is equal to stress divided by strain. And suppose you know what is strain and you want to calculate stress, you know the value of E, modulus of elasticity. So modulus of elasticity multiplied by strain will be stress. So how the stress is calculated? The stress is derived from strain using some relation like that. Primary variables are going to help you to derive other variables which actually required for us analysis, for our analysis. Uh, that parameters which are derived from the primary are going to be called as secondary field variables, right? So these variables are often referred to as the secondary variables because they are not directly calculated from the nodal unknowns, but are instead derived from the primary field variables. Like if I get displacement directly, then it is primary variable. From displacement, I can calculate strain, it is secondary variable. And from strain, I can calculate stress, that is also secondary variable. Like that. For example, these are the two examples given here. That structural analysis. Here you can see the table. In structural analysis, force is required to be calculated, but primary variable you are getting as a displacement. But if I use this equation, E into A into du by dx, du by dx is nothing but strain. multiplied by E, that is stress, and if it is multiplied to A, it will be force. So in this way, force is calculated by this equation. If U is displacement, I can use that here in the equation. You will get force. So displacement is primary variable and the force is secondary variable. Similarly, here in heat transfer analysis, temperature is directly received from the nodal displacement, and this T then after can be used in this equation. You must know this equation. What is that? Right? Heat plus K into A. So this equation actually is going to give you heat flux, heat transfer. So heat transfer or heat flux is secondary variable, whereas temperature is primary variable. So this is about the nodal unknowns and field variables. So we go for the next point in the syllabus, and that next point is coordinate systems. So this is very important uh, topic actually, very important concept, coordinate system. Not only for our case, but in general also, you must know what is coordinate system is. So anything which I want to measure, I want some references. Any position or location, if I want to show, I need some references. Suppose if I say that what is the approximate distance of Mumbai, at what distance the Mumbai is approximately. So most of the time, student used to give the answer that 150 kilometer to 175 kilometer, 200 kilometer, like that nearby. But in their mind, they think that I'm asking them to measure or the distance from Pune. They think that I'm asking the distance of Mumbai from Pune. I have not asked that question actually. I asked what is how far the Mumbai is. So the answer is multiple answers. Every answer is correct because I have not given any reference from where. So if I say from Mumbai, from Pune, then it will be the different answer. From Nagpur, different answer. From Delhi, different answer. From Kolkata, different answer. So you need some reference first. Then after you can locate anything. So that reference actually is called as coordinate system. In a plane, if you want to locate anything, you need in a plane you need two references. One we call as x-axis, other we call as y-axis. So what is the distance of that point from x-axis and what is the distance of that point from y-axis? That two values are actually going to give the exact location of that point. You can see the GPS system that we use for locating the points on the earth. Mostly when you send a location on WhatsApp through that map, it gives the GPS location theoretically to the receiver. That is GPS address. GPS location means we have used some coordinate system to locate the points on the earth, and you can find the degree, then minutes, and so on. Anyway, we are not going to discuss that in detail. Here we are going to discuss for coordinate system because we are going to make a model inside the ANSYS. We must have some coordinate system associated with that. Typically, three coordinate systems that we are going to use. And what are the three coordinate systems that we are going to use are: one is global coordinate system. The second we are going to call as a local coordinate system. And the third we are going to call as natural coordinate system. So what is these names or why that three different types of coordinate system that are used here? Generally, if you see the general coordinate system, we have Cartesian coordinate system, one we call it, that is x and y, x-axis, y-axis, Cartesian coordinate system. Another we call as path uh, coordinate system. Path coordinate system. So actually it is tangent and normal coordinate system. Actual name is tangent and normal coordinate system. We call that as path coordinate system. And third is radial and transverse coordinate system. Actually, the name generally used for that is polar coordinate system. So polar coordinate system and Cartesian coordinate system are the popular two coordinate system that we have. Now, the question is why there is a need of three different coordinate systems, whereas that all three are having some references and locating the particles. So, why that three? Because in general, I'm talking. I'm not talking for these three. In general, I'm talking. Why that three? That three because some coordinate systems, like Cartesian coordinate system, are helpful in some cases, whereas the polar coordinate system is helpful in some other cases instead of Cartesian. If I apply Cartesian coordinate system for that, it is very difficult and complicated to locate the things. Whereas the polar is going to help you very easily in locating that. In some cases, Cartesian is advantageous and polar is making it complicated. Or path is making it complicated. Cartesian is easier. In some cases, path is very easier compared with polar and Cartesian. So therefore, depending on what is easier, we used to go for using that coordinate system in general. Like locating the satellites, locating the astronomical objects. Polar coordinate system is very helpful. Whereas Cartesian is not going to help you. Cartesian means what is the reference x and y you are going to take for locating the sun. Okay. Anyway, so here also we have that the same concept is here that we have three coordinate system: global, local, and natural. So mostly natural coordinate system we are going to convert that global and local into natural, and then after we are going to use that for solving the problem. We are going to solve some problems also in this particular unit because sometimes numerical problem also asked in exam. And what problem and what type of problem that are asked, all that also relate, also depends on this coordinate system. Okay, take it very seriously. Now, if I go for one by one, so first global coordinate system. What is the meaning of that global coordinate system? The name actually indicates that global coordinate system is an external coordinate system that is fixed to a physical structure being analyzed to define the entire structure. In general, uh, I'll tell you what is global coordinate system is. Global coordinate system is nothing but having a single reference for whole body, whole part of a machine element or mechanical machine part, which we are going to analyze in the analysis. A single reference is there, and from that single reference, single means zero reference. From that point, I am going to measure 1, 2, 3, 4 in x direction, 1, 2, 3, 4 in y direction, 1, 2, 3, 4 in z direction. In this way, if the single reference, single zero point is there, and I'm measuring the everything in the mechanical element from that point, from that reference, then I'm going to call that as a global coordinate, right? Actually, the words here used here are fixed to the physical structure. That point is fixed to the physical structure. It is typically used to define the overall position and orientation of the structure, and it is also used to define the location of loads and boundary conditions. So before going in pre-processing, when you assign the force and assign the boundary condition, we use this global coordinate system for locating that. How? Suppose I want to apply the force on the beam whose length is say 5 meter. So I am going to give one zero position to that. From that zero position at 4 meters, suppose the force is acting. I am going to show that force at 4 meters. So in this way, for locating of loads or boundary condition where it is fixed at zero, suppose it is fixed at fifth 5 meter, it is free. So in this way, I will use global coordinate system for uh, location of loads, assigning the loads, applying the loads, and for defining the boundary conditions. Then the global coordinate system is usually represented using a Cartesian coordinates x1, as I said, x axis, y axis, and according to that, we show that. For example, I have shown that in the diagram, as you can see uh, in the slide, that this is y axis. If you can see my cursor, and this is the x axis. You can see, and suppose this is the truss. Do you remember truss? I think in engineering mechanics you must have learned this. So these are the elements of truss: 1 to 2, 3, 2 to 3, 3 to 4, and so. You can consider this as a stress, or you can consider this as a part of machine which is meshed. It is converted in some elements like one element, 1 to 6 one element, 2 to 6 one element, and so on. Right? Truss is actually a bigger form of element formation. You can understand the or understand and imagine the elements formation in case of machine by seeing that truss. Now you can see that x and y is shown here, and at one position here you can see that zero value is there, and everything then after will be measured from this zero. Okay. So if this all the points, if suppose I want to locate seventh point, I want to measure what is the distance on x direction. I want to see what is the measure on the y direction. Whatever the value that received, that will be global coordinates. That will be global coordinates. And now if I go for global coordinate system and showing that for 1D and 2D global coordinates, you can see here this 1D. Suppose I am using this line, vertical line, as a reference, and 1 to 2 is an element. 1 to 2 is an element, and this line is actually reference. And from the reference line, one point is at x1 distance, right? And second point is at x2 distance. So the length of element is x2 minus x1. Obviously, it is going to be x2 minus x1. So this now shown here, what x1 and x2 are global coordinates. Similarly, for 2D global coordinate system, here you can see here x and y are shown because it is 2D, and one point is having two coordinates x1, y1, 2 is having x2, y2, 3 is having x3, y3, and 4 is having x4, y4, x value and y value for that particular point. So these x1, y1, x2, y2, x3, y3, x4, y4 are global coordinates. These are called as global coordinates. Right. So let us go for local coordinates now. What is local coordinates? So I think we'll see this local coordinates and we'll keep what that natural coordinate pending for the next session, right? Because time will be over. So local coordinates means what? So local coordinates is simply measured at local positions. Simple. The local coordinate system is an internal coordinate system that is fixed to a specific element within the model. That means if I take the whole body, the global coordinate reference will be a single reference. But if I take out element from that body, element aside, and for element I am going to assign the reference. For that element I am going to assign the reference. Most of the point, one of the node of the element is 0 reference, and then after all other calculated. So for that element I have separate coordinates. Similarly, for the second element I will have separate coordinates. One of the node 0. Third element, one of the node 0, third coordinate. In this way, I have for separate coordinates for each element inside the body. So if such coordinates are there, we call them as local coordinate system. It is typically used to define the position and orientation of the element within the global coordinate system, and is also used to define the local direction of the nodes and boundary condition applied to the element. Are you getting this point? It is applicable to the element only, and it is going to give you the direction of loads on that element. What is the effect of overall load on that element? What is the direction of that load in that element? And what is the direction of boundary conditions, and how the boundary conditions are assigned to that element, or what is the effect on that, right? So it is typically used to define the position and orientation of an element within the global coordinate system, right? So there will be some relation between global coordinate and local coordinate. We can create that. The local coordinate system is usually represented using a set of orthogonal axes that are aligned with the element geometry, right? What is the meaning of that? I'll show you. Suppose this is one truss again, as we discussed previously. 1, 2, 2, 3, 3, 4, 4, 5, 5, 6 are, then 2, 5 also, then 3, 6 also, and 2, 6 also, 3, 5 also are the truss, elements of a truss. And suppose if I want to give the coordinates to 1 to 2 element, 1 2 element, you can see here 1 2 element inclined. So I am going to give one perpendicular direction, suppose as a y direction, and second x as aligned to that 1 to x direction. So this is the local coordinate assigned to that 1 2 element only. So 1 is 0 and 2 is having some certain position like that. Similarly 1 6, where is 1 6? This is 1 6. So here 1 6 is given. So 1 is taken as 0 and 6 is having some certain dimension in x direction. Similarly 6 2 here. Here y is considered and along that x is considered. Though here 6 is now 0. So in this way, if you are assigning the local coordinates to each element, then they are called as local coordinate systems.